Welcome. We want to consider rules of inference for propositional logic, and there are 8 of them that we're going to look at. So the first one that we're considering is called modus ponens. This is a very common approach to writing a proof. Yeah, that's what we're interested in doing in future sections. So again, rules for inference allowing, or rules of inference allowing us to construct these proofs that we will eventually do. So we have a particular tautology, right? Tautology means that it's always true. So P and P implies Q implies Q. So this is always true, right? Because it's a tautology. So what we want to do is we want to use this idea that if both of these are true, that implies Q. So, and if both of these are true itself, right. So the idea is that we actually want to demonstrate or assume truth depending on where we're at in our construction here. I guess that construction is for construction of proofs later. But if we take the statement, it is snowing, and I will study discrete math. Statements themselves can be evaluated as true or false, right? Propositions. This seems a little bit weird. So we're right. I will study discrete math. How do I evaluate that as true or false? Well, the point is, when we are working through these, that we are assuming that this is true and that this is true, right? We're assuming that our premises are true, and we're deciding if that allows us to say that the conclusion is true, right? That's the goal. So overall, this tautology is true. So, right, if it's not snowing, then overall this disjunction is false, and because the disjunction is false, we get that the implication is true. So that's why it's a tautology, right? Or that's one of the instances of observing its truth value of truth. But what we want to do is we want to observe explicitly that Q is true. That is our interest here, right? We want to conclude that Q is true. Now, since it's a tautology, if we want to conclude that Q is true, that can only happen when this is true. So usually we demonstrate that P is true and that the implication is true, and therefore we can conclude that Q itself is true. Okay, that's the practice or the implementation in a proof. So it is snowing. That's P. If it is snowing, then I will study discrete math. So we're assuming that that is also true. All right. If I know that it is snowing, and if I know if it is snowing, then I will study discrete math. Right. But both of those are true. Then the only way that this can be true when this is true is when I will study discrete math is true. So therefore, it must be the case that I will study discrete math. So we're going to use these ideas, these rules of inference. All right, so there are 8 of them. Let's try to walk through them a little bit more quickly here. So we have modus tollens, not Q, and P implies Q implies not P. So if if we have an implication or a conditional statement, P implies Q. If this is false, the only way that the implication can be true is if P is also false here. So what we're interested in, right, implication is false when this is false or both are true. So the only way that we can have not Q true and P implies Q true is when P itself is not true. So therefore not P. So it is snowing, and I will study discrete math. So looking at the same example here, if it is snowing, then I will study discrete math, and I will not study discrete math. Well, the only way that that can happen is if it is not snowing. So we have our, we assume these are both true, and it doesn't matter what order we say them in, right? Because it's an and. I can write this one in front of that one, and that's fine. So, right, and in fact, that's what we've done here. They wrote the implication or the conditional statement prior to the not Q. All right, so if it is snowing, then I will study discrete math. Excellent. I'm assuming this is true, but I'm not going to study discrete math. Well, the only way that this can be true, right? The only way that this conditional statement can be true when I'm not going to study discrete math is if it is not snowing. So I conclude it is not snowing. I conclude that that is true. Hypothetical syllogism. So the corresponding tautology is if P implies Q and Q implies R, then we get that P implies R, right? So this is it's sort of a transitive property. We want to move from P, P goes to Q and Q goes to R, so we want to get that P goes all the way to R, right? So we see this sort of a transitive property here, and we like that. So again, hypothetical syllogism. So let P be it snows, let Q be I will study discrete math, and let R be I will get an A. So we're going to assume these two things here. If it snows, then I will study discrete math. If I study discrete math, then I will get an A. Therefore, if it snows, I will get an A, right? So this should make sense for us. If it snows, I'll study discrete math. If I study discrete math, I will get an A. I'm not saying that it is snowing. I am not saying that I am or am not studying discrete math. I'm not saying that I am or am not getting an A. I'm still ending up with an implication or a conditional statement. If it snows, then I'll just study discrete math. If I study discrete math, I'll get an A. Therefore, through this transitive property, if it snows, I'll get an A. All right, disjunctive syllogism. So P or Q and not P. So if P or Q is true and not P is true, well, if this or that is true and I know this is false, then it must be that this one is true. Okay, that's what we're looking at. I will study discrete math. I will study English literature. For our two statements here, I will study discrete math or I will study English literature. Excellent. But I'm not going to study discrete math. Well, if I'm going to study one or the other and it's not going to be this one, then it has to be that one. Excellent. Right? Assume these are true and we conclude that this is true as well. Addition. So P implies P or Q. If P is true, then of course P or Q is true. That's should be fairly obvious, I think. So that PB, I will study discrete math, and let QB, I will visit Las Vegas. All right, I will study discrete math. Excellent. That's what we're doing right now. Therefore, I can certainly say that I'm either going to study discrete math or visit Las Vegas. All right, I'm assuming that this is true. Our premise. Will you go to Las Vegas? Don't know. Don't really care. I know you're going to study discrete math, therefore I can conclude that one or the other is true, because I know that one of them specifically, that you'll study discrete math, is true. Excellent. So simplification, if P and Q is true, then of course both of them are true, so I may conclude that either one of them is true. So if P and Q is true, then certainly P must be true. I could also have said if P and Q is true, then Q is true, but it's the same difference, right? This is what you could call it, commutative, that the order that I write it in doesn't matter. So really, they both say exactly the same thing. Anyway, let P be I will study discrete math. Let Q be I will study English literature. So I know that I'm going to study discrete math and English literature. I will study both of those. Therefore, yes, of course, I will study discrete math. Awesome. Conjunction, corresponding tautology here. Oh, interesting. I wonder why they put parentheses around that. I wonder if there's a little bit of an error here. This seems very strange. All right, well, it seems very strange. I was able to verify that this is indeed what we mean here. If I know that P is true and I know that Q is true, then I know that P and Q is true. No surprise. I think we'll move on from that. All right. So a resolution here, P or Q is true and not P or R is true. Then we have that Q or R is true. How can we think of this one here? So P or Q and then not P or R. So P and not P can't both be true. If P is true, then not P is false. If P is false, then not P is true. So if we assume that P is true, then not P is false, and we have that R must be true. If P is false, then Q is true, so I have that Q must be true. So either way, right, if I have P and I have not P, then if both of these are true, then either Q or R must be true. So I think this makes sense, but let's look at this example. I will study discrete math. I will study English literature. I will study databases. I will study discrete math, or I will study databases. I will not study discrete math, or I will study English literature. Excellent. So what I want to recognize is, let's see here, place our line, assume that these are true. Therefore, I will study databases, or I will study English literature. How do we make sense of this? Let's see here. I'm assuming that it's true that I will study discrete math or study databases. Excellent. If I study discrete math, that makes this true, which means that this part is not true, and I will also be studying English literature for sure. If I do not study discrete math and I choose to study databases, then I have chosen to not study databases, and I don't know about this. But in both of those cases, one of them, right, I did one of these. I either studied databases or I studied English literature, depending on whether I studied discrete math or not. Excellent. I believe that is it for our rules of, let's see here, what did we call them? Rules of inference. Excellent. So join me and we will take a look at using these rules of inference to construct valid arguments.